Good afternoon to everyone who is registered here. Thank you for joining us today. It's really our pleasure to be here as part of this special webinar organized by DSS Imagetech in celebration of World Microscope Day. Um, my name is Peter Lang. I'm joined by my colleague Matt Fay here. And today we're going to be introducing the SLICE light sheet system. Light sheet really has become a powerful tool for volumetric imaging of large biological specimens, especially in areas like neuroscience, developmental biology, ecology. However, many traditional light sheet systems require significant infrastructure, complex alignment procedures, and a very substantial financial investment. The goal behind our slice light sheet system was to rethink how this technology could be delivered in a more practical and accessible format. So today we're going to introduce the imaging technology behind SLICE, walk you through the system workflow and an actual acquisition, and also highlight some of the applications where this approach is enabling insights into volumetric imaging experiments. So just briefly go over the concept of light sheet itself. Uh, Light sheet microscopy works by illuminating the sample with a thin sheet of light that intersects the detection plane. This allows us to image an entire optical plane at once while minimizing photo bleaching and out of focus light. However, traditional light sheet systems often require large optical tables, complex alignment procedures, and specialized expertise to actually maintain and run. That complexity and cost of a traditional commercial light sheet system, as well as fragmented workflows, has really limited access to this technology for many labs. SLICE was designed to remove those barriers so even non-experts can generate quantifiable 3D image data sets like the one you see here. This is actually generated by one of our collaborators, Dr. Roger Tomer. So let's talk a little bit about the technology used in the SLICE system. Anyone that's somewhat familiar with light sheet microscopes, you know that there are many different types of light sheet systems out there. Open top light sheet theta microscopes, single objective light sheet microscopy, axially swept light sheets, lattice light sheets, and it goes on and on and on. SLICE is the next iteration of a system that was detailed in a peer-reviewed published paper by Dr. Raju Tomar, our collaborator at Columbia University. MBF and Dr. Tomar designed the SLICE system as a high-performance light sheet microscope in a very compact, cost-effective platform that dramatically reduces the mechanical, optical, and electronic complexity while lowering the overall system costs by orders of magnitude. In short, we wanted to bring light sheet to the masses and provide a simplified pipeline from acquisition to publication-ready quantifiable data. So how do we simplify light sheet microscopy while still maintaining high performance? The key really is this concept of projected light sheet microscopy, or PLSM. In traditional light sheet systems, the illumination sheet is generated by using specialized optics such as cylindrical lenses or scanned Gaussian beams, single mode lasers. These configurations often require very careful alignment, mechanical stability, and utilize very expensive components like those single mode fiber lasers. In PLSM, the light sheet is actually generated through projected illumination patterns rather than fixed optical shaping elements. So this approach allows the geometry of the light sheet, such as thickness and its position, to be controlled digitally. And this is kind of the I would say what the unique feature about PLSM. Because this illumination pattern is generated computationally, the system becomes far simpler from an optical perspective and much more robust mechanically. This innovation is really one of the key reasons for the Slice platform and its ability to be implemented as a compact benchtop system rather than a large custom optical setup. So here you can see an example of the light path. This is actually from Dr. Tomer's paper. It's quite simple. We have our projector element. This is our proprietary light engine going to a tube lens, then through an objective generating the light sheet. And we have a simplified detection pathway here with our detection objective. We're using a motorized filter wheel in place of the multipass filter in the original paper, and then a backside illuminated SCMOS camera. So here we see an example of the system itself. This is the Slice system, and building on this concept of projected light sheet technology, the Slice system really brings together an entire workflow into this compact, truly benchtop platform. It integrates the dual opposing projected light sheet, which improves illumination uniformity and penetration through clear tissue. The system also incorporates this concept of dynamic refractive shift correction. So it can accommodate multiple clearing protocols without any hardware changes or complex alignments. On the computational side, Slice includes an end-to-end pipeline for automated acquisition, tile stitching, image enhancement, filters, and high-performance 3D visualization, all within the same Bright Slice software environment. This combination means that researchers can go from intact, clear tissue to fully visualized 3D data sets without needing any type of specialized optics or extensive computational expertise. Importantly, the entire system is available as a turnkey solution starting at under 100K, which makes this high-resolution volumetric imaging accessible to labs that otherwise would be excluded just due to high cost and complexity. As an added bonus, we have included a free 3-month trial of the MBF Light Sheet Suite, which is a series of our analysis products for quantification of the Slice image data as well. In developing Slice, we made several key improvements over the original PLSM design to enhance the speed, precision, and image quality of the system. We implemented a proprietary light engine for faster scanning and integrated rapid sample positioning using a precision piezo XYZ stage. This allows us to acquire larger volumes more quickly without sacrificing resolution. The system also features improved spectral separation using a motorized emission filter wheel, which enables seamless acquisition of multiple fluorophores with a very user-friendly built-in workflow. Optical design improvements extend the high-quality image across a larger field of view, while the use of a backside illuminated camera, very high QE, camera enhances the sensitivity for low fluorescent signals. Finally, actually building on the recent work of Dr. Tober's lab, this 2024 preprint he is shown here, we implemented a corrective optic in the detection pathway, which improves the image uniformity and reduces aberrations, particularly useful when scanning very large clear tissue samples. Together, these enhancements make SLICE faster, more sensitive, and more reliable for high-resolution volumetric imaging. This achievement was recognized with the 2025 Microscopy Today Innovation Award for its impact on advancing light sheet microscopy in general. So let's talk a little bit about the actual specifications of the system, the hardware design. The design changes that we just mentioned enable SLICE to have the following characteristics. So for illumination, the platform supports 3 excitation channels at 455, 520, 640 nanometers. These wavelengths align with common fluorophores, allowing for 3-channel or even more acquisitions. And the system, as mentioned, utilizes a dual-arm light sheet setup, producing a light sheet that's approximately 5 to 8 microns thick, depending on how we set the system up, across a field of view, roughly 1.2 millimeters by about 0.75 millimeters, using the 10x objective. So here you can see this is the field of view associated with the 10x. We also have a 5x objective option. This is showing you here the relative 5x field of view as well. With the 10x objective system, we basically have a lateral resolution down to approximately 3/4 of a micron. Samples are mounted in a cuvette configuration, so that's shown here. This allows imaging of specimens of about 20 by 20 by 18 millimeters in size, which is sufficient for many clear tissue preparations, including whole mouse brain, or large intact organ sections. This cuvette-based sample mounting also reduces the volume of clearing and refractive index matching media required. So this lowers the reagent costs while maintaining optimal imaging conditions. Whoops. And just wanted to mention the system here is truly a benchtop system. It's on the order of the size of, say, like a microwave oven, if you will. That concept of dynamic refractive shift correction allows us to support a wide range of clearing methods, from aqueous to solvent-based protocols such as iDisco, clarity, cubic, binary, and so forth. So this is really a unique feature of the SLICE system itself. The fact that you can image many different types of samples without making any hardware changes to the system at all. Just want to briefly highlight the fluorescence detection capabilities of the system. As mentioned, the SLICE platform has 3 excitation channels, which correspond to blue, green, and red spectral ranges, commonly used in biological imaging. These excitation wavelengths are paired with optimized emission filters in that motorized emission wheel that allow for detection of many widely used fluorophores. For example, in the blue channel, we can image GFP, CFP, Alexa 488, commonly used in viral labeling and reporter mouse lines. The green channel supports dyes such as Alexa 546, 555, Sci3, TD Tomato, which are frequently used for immunolabeling and neuronal tracing. Finally, the red channel enables imaging of far-red fluorophores such as Alexa 647, Sci5, ToPro 3, which are particularly useful for nuclear staining and deep tissue imaging in clear samples. Just as an aside, while this slide is up, you can see an example of a data set acquired on the SLICE system playing in the background. That is mouse brain cortex expanded roughly about 14 times, imaged with the 10x objective. The sample is GFP with secondary Alexa Fluor 488 amplification. So yes, we can work with expanded tissues as well. The system is very flexible with the types of samples it can image. Now, I've brought up this concept of this dynamic refractive index correction a couple of times. I want to show you an example of how this works. So on the left side, you'll see a video playing. This is without the refractive shift correction enabled in an iDisco sample going through a few millimeters of tissue. And as you can see, as we go through the tissue deeper and deeper, the cell bodies become less focused. Whereas on the right-hand side here, with our dynamic refractive shift correction enabled, as we go through multiple millimeters of the sample, the cell bodies stay nicely focused throughout. And again, this is done in real time. This is not a post-processing technique. This is actually a optical correction that is enabled during the acquisition itself. Okay. This correction is implemented through software-controlled optical offsets, meaning there's no hardware modifications, no system reconfigurations, or any type of alignments are required when you're going between your different protocols. In practice, this allows researchers to image samples cleared with a wide range of methods while maintaining consistent optical sectioning and image quality without needing to retune the microscope. Here's another example of a clarity cleared tissue sample. So this has roughly a refractive index of 1.46, whereas the sample we were just looking at was around 1.56, so a significant refractive index change. And here again, you'll see the cell bodies and processes on the left go further and further out of focus as we go deeper into the tissue. On the right, same field of view imaged with correction enabled. And as you can see, we can go through the entirety of the sample and not lose any focus of the cell bodies or the dendritic fibers as you go through the sample. And again, this is a real-time correction accomplished during the acquisition itself. Now I'd like to, show you a few representative data sets acquired with the SLICE system, just to illustrate the range of potential biological applications. So starting with the top left there, that's a phosphotrap mouse brain expressing TD Tomato, cleared using the cubic R protocol. Let's see, in the top right, we have a mouse embryo where the serotonergic neurons labeled with Cy3 are shown in orange, and the tissue autofluorescing is shown in cyan. This sample was actually cleared with iDisco. On the bottom left, we have some human tissue. Actually, this is a data set that shows vascular imaging in neurotypical post-mortem human brain sample processed using Chanel clearing method. So here we can see intact vascular networks. On the bottom center, we have a zebrafish larvae brain at day 6, showing the synaptic density in cyan and GAD65 enzymes in magenta. And finally, on the bottom right, this is a brain of a Mexican cavefish. This is cleared with iDisco and labeled with TOPRO3 nuclear staining. So as you can see, all different samples, all different clearing techniques, all imaged with the same system without making any changes whatsoever to the hardware. You simply drop in whatever sample you want to image, and you could achieve results such as this. All these movies that you're seeing were actually generated by the Bright Slice software as well, which I'm about to talk about right here. So, acquiring the clear tissue data sets generates extremely large image volumes. So efficient data management and visualization are critical. To address this, Slice platform integrates an end-to-end computational pipeline through the Bright Slice software. So Bright Slice is included with every Slice system. It's everything you need to control the microscope with very easy to use workflows that we're going to see shortly with Matt. So basically, this allows the system to be operated very easily by novice users. We have 3D stitching, post-processing filters to take your multi-tile acquisitions and create a single final seamless image, one image. The visualization tools for inspecting and generating publication-ready images or movies are built right into this software, so you don't have to bounce around, like I mentioned, with these fragmented workflows, pulling together other pieces of software to get to your endpoint. And in particular, the software also includes a very efficient data storage and management pipeline that keeps your data safe and accessible. We use a JPEG 2000 image format that, by default, that allows for compression of images without introducing any types of artifacts or changing the quantifiable nature of the data. This can basically take your data set of multiple terabytes and compress it to a few hundred gigabytes or less even. So once these volumetric data sets are acquired, they can be integrated with some of our downstream analysis tools to extract quantitative biological information. So Slice feeds right into our other image analysis software very seamlessly. And as I mentioned, when you purchase a Slice, you actually have 3 months, 3-month trial access to these various analysis products, such as NeuroInfo, so for registering brain images, to the Allen Brain Atlas, and detecting cells by region. The NeuroLucida 360 software allows you to reconstruct complex neuronal morphology. You can analyze and reconstruct vasculature using VesiLucida 360. And we even have our Stereo Investigator software that's been updated and to support these large clear tissue data sets with new stereological probes, so you can accurately estimate population, length, volume with those tools. All these tools are available to explore during the trial. One thing I did want to briefly touch on also is this concept of the Slice Discovery platform. And here you see an example of the Slice system itself. But to create an even more efficient system, we offer this Slice Discovery platform, which consists of four major components here. We have the slice system itself, a slice analysis workstation, uh, a NAS storage system, so a network attached storage device. Uh, and this is all coupled together via a high-speed 10G network. So these four components are put together in various packages to match the needs of your particular lab or core facility. Um, and this, what it really does is allow for more efficient, faster processing of these large data sets. So despite the tremendous value of light sheet microscopy for volumetric imaging, widespread adoption has historically been limited by several practical barriers. Traditional light sheet systems are expensive, costing hundreds of thousands of dollars. Uh, they frequently require specialized optical infrastructure and expert operation. Uh, what we really tried to develop here is to lower those barriers and make high resolution, clear tissue imaging more accessible to the broader research community. So Slice is really designed to be this compact benchtop system, providing you with a very flexible, complete light sheet solution at a cost significantly lower than any other traditional open source or commercial system out there. At the same time, our platform integrates automated acquisition, data processing, and dynamic refractive index correction, allowing researchers to image samples cleared with any protocol without requiring any types of hardware changes or optical adjustments. And the system, the result is a system that really brings together high resolution volumetric imaging within the reach of many more laboratories. Effectively, we're looking at this system to be the workhorse system of your lab. Similar to like a typical wide field fluorescence microscope is routinely used in your lab. You can now have your own personal light sheet system in your lab for roughly about the same cost. So with that, I'd like to thank you for your attention for the PowerPoint section of the presentation here. And I'm going to hand things off to Matt so he could show us some actual acquisition using the system and the Bright Slice software. Matt, take it away.
Great. Thank you, Peter. Let me just change my camera here briefly. So now we're looking right inside the Slice microscope system here. And what I actually have on the system right now is that sample that we were just looking at, that sort of rainbow pseudo-colored video that Peter was playing. This is a 2 centimeter by 1 centimeter cuvette. And you may or may not be able to see the mouse brain in there. It is fairly clear. But really day to day, your interaction with the actual hardware is really just taking your sample, and we're going to go right up to this magnet attachment to the stage, and we're just going to clip it on there, and we're good to go with the system. Pretty much everything else you're going to do with the Slice is controlled through the software interface itself. So I'll go ahead and now share my screen. And Peter, if you could let me know when that actually loads, that would be great.
It is now up. Yes.
All right. So this is our software interface for controlling the Slice microscope system. This large area, dark area, is where our live image is going to show up, or any acquired image that you open in the software. Just to the right here, we have a pretty standard Z meter that tracks our positioning in our Z axis. This panel here is our Slice light sheet controls, and is pretty much where we control most of the hardware of the microscope. We have a quick drop down for selecting your emission filter. These sort of green buttons, enable left and enable right, these are master controls over our left and right light sheet. As Peter mentioned, we have dual-sided illumination. You can see on the microscope here, this is one of our illumination objectives here, and the other is on this side here. The detection pathway is actually behind this oil reservoir here, and feeds out the backside of the system. So with these controls, we're able to turn off the left light sheet and just work with the right light sheet, or turn both on at the same time, or vice versa, only working with the left light sheet. Down below here, we have 3 excitation wavelengths on the slice. We have a 455 blue nanometer excitation, a 520 green nanometer excitation, and a 540 nanometer red excitation. We can control the diode intensity of each one individually, and we can turn each individual channel on. I'll turn on the green, and you may be able to see that our light sheet is now passing through our media reservoir there. Down below here, these settings that we have for the individual light sheets, we have a left light sheet offset and a right light sheet offset. And this is how we're going to perform that refractive index compensation that Peter was describing earlier. What we're really doing is, if my hand's the light sheet, we're moving the light sheet closer to and further away from the detection objective to compensate for the shift in our detection focal plane. So wherever we are in the sample, our detection focal plane may have actually changed its position based on the working distance from that refraction. We're going to move the light sheet to fall in that detection focal plane for that positioning in the sample. We'll then set up a few points of focus throughout the sample and interpolate between those points of focus while we're imaging live and automatically while we're doing the acquisition. This panel here is our refractive index compensation tool. So this is where we're going to add points of focus to our refractive compensation map, as we call it. We make these maps on a per channel basis. You'll see that the 1, 2, 3, 4, 5, 6 in this tool here corresponds to the 1, 2, 3, 4, 5, 6 in our multi-channel control presets. You'll see that I have my green preset here activated. This is where we're going to save our emission filter, what light sheets we're using in terms of the left and the right or both, our excitation color, as well as the excitation intensity, and any offset and camera settings like our exposure and gain all get saved to these presets, so that once we have them set up, all we need to do is click a button to set everything up automatically. So once you have this set up, if you have a multi-channel sample, all you need to do to switch between the channels is just single click of the button. Here I'm going to lower our sample down into our focus position here. You'll see when we first get on the microscope, you may see some signal, but things will likely be out of focus. That's okay. All that really is where we are in the sample right now. Our light sheet is not at the same position as our detection focal plane. We're either a little bit above our detection focal plane or a little bit below. And as we get closer and closer to that detection focal plane, objects and structures will become more in focus. So when I first get on the microscope, I find an area where I can see signal, but it's a little bit out of focus. What I'm then going to do is I'm going to isolate one of my light sheets. So I'm going to turn off my left light sheet here. And I'm going to go down to my right light sheet controls, because I'm working with the right light sheet. And I'm going to adjust this offset setting. If I select this box here, it will actually tie the mouse wheel of my mouse to this setting and allow me to scroll through the focus. So you can see here, I'm kind of scrolling my light sheet through the sample, and things are starting to come more and more into focus. Once I'm in a position where everything's looking crisp, I can switch to my other light sheet and repeat the process. Once I have both light sheets focused, I'll turn both back on, and I'll toggle between my light sheets, turning one on, turning both on. what I'm making sure here is that I'm creating the same image with both of my light sheets. If I wasn't creating the same image, I would see new structures populate. And what that indicates to me is that my light sheets may not be actually coplanar with each other. They may be in our axial or our Z axis may be stacked on top of each other. And what that's going to produce in the resulting image is actual doubling of the structures, which we want to avoid if we're acquiring with two light sheets. So here, I should see structures get brighter, but I don't want to see new structures populate. And it seems like we've achieved that. So I'm going to go down here. I'm going to select my refractive index compensation map that corresponds to the green channel I'm working with. And I'm just going to add that point to my map. I'll then navigate in our Z-axis. And as you will see, this sample is actually not as RI mismatched, but as we go deeper into the sample, we'll start to lose resolution a little bit. And what we can then do is repeat that process we performed before. So I'm going to turn off my light sheet. I'm going to adjust my left light sheet here. And you can see the left light sheet as we go deeper and deeper into this mouse brain. We're actually on the side of the mouse brain that's closer to the right illumination, so it makes sense. That's actually a good example of why we have these dual-sided light sheets. When you're closer to the illumination objective that you know is passing through less tissue, that will contribute more illumination and signal to the image. So here I've adjusted my left and right again so that they're coplanar and creating the same image. I'll add Z. And now I can turn on my use interpolation map. Now, wherever I go in the sample, we are going to adjust the light sheet's position so that we maintain crisp focus throughout the sample. Throughout the software, all down this left panel here, we have these markers that we can actually drop within our environment. I can select a marker and I can just click and drop it. It's very helpful as you're navigating around the sample. Say you find a region of interest that you're interested in, you can drop a marker on them. Now, as we navigate around the sample, say I'm way on the other side of the brain here looking at something else, but I want to go back to that region of interest. This macro view tool down here tracks all of our markers in our environment. And I can use this go to feature to return to a marker of interest. I like to use these markers now that I have a map set up that I can actually drive around my sample and everything will maintain focus to actually set up our delineation of our sample. Where do we want to scan? So say I was driving around and I found the left side of my mouse brain and maybe I should actually move in Z to make sure that it doesn't extend out that way. But once I have the widest extent of my mouse brain, I could actually take a marker and drop it there and return to it later when we're actually setting up in the workflow. So as I'm exploring my sample, I like to, drop markers wherever I am, just so that I can return to them and it helps me start delineating the sample. Once I've moved around and I know that my sample's in good focus here, I can actually jump into our tissue scanning workflow that will take us through step by step setting up this multi-tile, multi-field of view acquisition of the entire cleared tissue sample, or whichever region of interest you would like to acquire. Here in the first step, I'm going to turn my excitation light off because we don't really actually need it anymore. I've already delineated my area that I want to scan with my markers. I'm going to scan the extensive placed markers here is how I'm going to set up my scan. I'll go to the next step and it will prompt me to place a marker on the left edge of the region. I'm going to go to my orange marker that represents my furthest left extent, and I will place a marker on top of it. It will now tell me to use the top edge of the region. That's this marker up here. And we're just going to work in a clockwise orientation, going through these markers until we've delineated our XY area for our scan. Once I have that delineated, it will show right up in my macro view. This is the area that we're going to scan over. I can go on to the next step here, and what we're going to do is actually delineate where is the top and where is the bottom of our scan. So I'll work my way up here to the top of our sample and set it. I'll then go back down through the sample to where I want the bottom, and I'll set that there. We can then choose what is our distance between planes. I have this system configured with it's about a 7.5 to 8 micron light sheet. 5 microns gives us sufficient spacing. In this next step, we're going over some of the ways that we can actually acquire with the slice. We can select to use the current channel settings. That's going to use whatever's saved in these presets down here. And what that corresponds to is we're either going to acquire with just the left light sheet, just the right light sheet. Where that's advantageous only using one light sheet is you don't really have to worry about having your light sheets coplanar. Um, so for very small samples where you don't need dual-sided illumination, something like a zebrafish larvae or something on that sort of 1 millimeter scale, you can very likely use only one light sheet. So either the left or either the right. Another scenario is maybe you want to acquire with both your light sheets, like we're going to do here. That can help compensate for some striping artifacts that are very common to light sheet imaging. These are occlusions of objects or maybe contaminants on the surface of the sample that just cast a shadow through your sample from the light sheet, and that will actually appear as kind of a stripe through the image in your resulting image. Um, so there's that way we can acquire with both light sheets as well. Both of those correspond to using the current channel settings. But the other way we can acquire is we can actually split our region down the middle or actually at a set point. So where this is really advantageous is if you have a mouse brain that's not cleared very well or a very large sample like an intact rat brain, the light sheet that's passing through the most tissue may just be contributing scattered illumination to the image by the time it reaches that far side of the tissue. So in this scenario, we would use the right light sheet for one side of the tissue and the left light sheet for the other. For this acquisition, we're just going to use both light sheets at the same time. This next step here is reminding us to set up one of those compensation maps. We've already set up the map, but say we were driving around there and we noticed that some points were out of focus. We can actually add or correct our map at this point. The other thing worth mentioning is for these maps, for a well-cleared, homogeneously cleared sample that has a homogeneous RI throughout it, typically, and I would say 98% of the samples I've come across fall into that category. We typically only need to do this refractive index compensation over the z-axis, over the depth of our sample. But it's worth mentioning that if you do have a sample that's more difficult to clear, more difficult to get to that homogeneous RI, we can make these refractive index maps on an XYZ 3D interpolation basis. For this one, the Z map that I set up earlier, I think is sufficient. So we're going to go to the next step, which will actually just remind us to add points to whatever map we're using if we haven't. We already have, so we'll just continue on. In this step here, we've done most of our setup of our acquisition so far. And when I'm doing my setup, in case I get talking to you or someone else in the lab, I like to use low illumination intensity and a high exposure. That's going to prevent me staying in one area and maybe causing photo bleaching to our sample. So while I've been setting up there, I've actually been using a very low illumination power, 13% of our diode intensity, and an exposure of about 121 milliseconds. But when we actually run the acquire, it's definitely safer to go with higher illumination power. And we really want to minimize our exposure time to maximize our acquisition speed and how long this acquisition is going to take. So I'm going to go down to about 17.2 milliseconds for this sample. We'll see we lost a lot of signal there, but that's okay. I'm going to bring our diode intensity up here. You can see we start to maintain some signal. You can see it looks really grainy. I now have new settings for my camera. So I'm actually going to need to, sorry, I forgot to save that. I'm going to implement some of our camera corrections, like a fixed pattern noise correction and our dark field correction. And that's what's going to happen in this next step now that I've set up what I'm going to image with. I'm going to turn my light off here and I'm going to close the door to the microscope. I have my dark field correction and my fixed pattern noise correction checked. I'm going to go to the next step here, and it'll remind me to close the door of the microscope. I'll hit OK, and it's just going to run through the operation calibrating those corrections, and now our corrections are applied and ready to acquire with. This next step that we've moved to is an opportunity to take a quick sample acquisition. If you're acquiring an entire mouse brain that may be hundreds or 150 fields of view, um, it's nice to use the settings and the presets and the mapping that you've set up to take a quick 2x2 or 3x3 field of view acquisition, just to see that all those settings are set up the way that you expect them to be, and make sure the image is coming out to your liking. This next step here covers some of the post-processing filters we have built into the Bright Slice software. These can all be turned on in the actual post-processing stitching steps, as well as after you've saved the image as well. We have them here in case people have already parameterized those and they're working with a cohort of the same samples. They can actually turn them on at that point. In this final step here, we're just going to choose a save location. So when you're acquiring, it's always important to acquire to the local storage that is in the computer that's controlling the microscope. It's locally attached to the microscope. That's going to be the most reliable and the fastest for our acquisition. That being said, these cleared tissue acquisitions can get into the multi-terabyte range. So very large acquisitions. You may not have a local drive large enough to support the acquisition that you're doing on that local system. What we can do here is we have a companion software that we call CopyFile. CopyFile will act as a secondary save location on a network attached storage device or a different processing computer in your lab. So what we're actually doing is we're acquiring the image to our local drive. Our CopyFile software behind the scenes will come in and take that file and copy it to your network attached storage device or other storage location. We then also have a setting that allows CopyFile to actually go back in and delete the file off of that local drive, freeing up space for the rest of the acquisition. For this acquire, though, I'm just going to acquire to the actual local save directory. Before I kick things off here, I like to just trigger my preset, make sure everything's coming up the way I expect, and then I will start our acquisition here. So this acquisition here, we're doing about a 1x30 scan with 400 planes. And this scan here would take us about 20 minutes. I have already actually acquired this sample, so we're going to cancel this scan and do a little bit of a cooking show demonstration for you. So after that completes, we can jump into our image stitcher here. This is how we post-process our acquisition. I will jump into this sample here. I'm just going to turn that off. So this is actually our acquisition. So once this is the region that we just acquired. You can see it lines up with those orange markers pretty well. Um, we have those two filters that are built into our post-processing steps here. We have a rolling ball background subtraction and a flat field correction. The flat field correction is intended to bring out any tiling artifacts, kind of the checkerboard pattern that you may see in some of these multi-tiled field of view acquisitions. Here we don't have much tiling, so I would actually skip turning that on. What I do like to do for this image or this sample is I actually used our rolling ball background subtraction. It's a pretty standard rolling ball algorithm. You actually set the diameter of the rolling ball, and it will apply it to your image. We have different save resolutions we can turn on. We can actually downsample the image. Sometimes Slice has more resolution than you actually need. It's very likely that if you were just detecting somas in this sample, you could very likely downsample this by a factor of 4, and be a quarter of the resolution without affecting your imaging result. That translates to a smaller file, something that's easier to work with in analysis and things like that. These are the data handling aspects that we have built into the software to make things easier for you and your pipeline. Um, Finally, we want to do our advanced XYZ stitching. This is going to take every image tile and perform image registration between the intersection of the tiles, making sure any fibers that run between our images line up very well. I'll then stitch this into a single file. These quick focus positions just give us the ability to go through our sample and just check out what's going on. And the last thing I would do is then start processing the image. This image would save in about save and stitch in about 3 minutes. But I already have done that here. Oop, don't double click it. We want to drag and drop into our environment. And here is our acquired image. I'm going to map this to one of our, we have some color maps that are actually based on the intensity in the image that actually look great to visualize. I actually like this one down here, red hot. There we go. So in our 2D environment here, I can actually go through the planes of our acquisition. We can jump by 10. So we can interact with the image in a 2D format. But I think the more interesting way to actually visualize this data is in 3D. I'm going to give us a little more intensity here. And we'll open up in 3D. Quick representation of the image, and it will load to its full resolution as we go here. And you can see that's the image that we just acquired in about 20 minutes there. It's about the top of the hippocampus in the mouse brain. You can kind of see that interlocking C there. We have partial projection filters or features, so we can thin this out. It can be a little chaotic to look at an entire mouse brain all on its own. But this is really the image resolution that you can expect from the Slice Light Sheet microscope. Plenty of resolution to reconstruct those fibers, detect cells, do various brain mapping and atlas registration. Another great feature that we have in the software, if this is an entire mouse brain, things can be rather chaotic in a really large data set. We have this subvolume feature that you can actually drag, resize on a smaller region of interest in your image. And we can just open up that portion of the data set and actually work with that. We can also save this as a crop. So if you have an entire mouse brain and you want to put it on a thumb drive and bring it to a conference, just a small ROI, this is a great feature for that, as well as a great feature for breaking up your very large acquisition into smaller portions that are more manageable for analyzing. As Peter mentioned, we also have that movie maker. Works very similar to standard movie makers where you just add clips, rotate around, and we can export a movie so that you can represent your data set. So I think that concludes our demo of the instrument. Love to open it up to any questions anyone has. And thank you for your attention and attendance today.